All right, let's wrap up all we're going to do in chapter 14 with 14.3, talking about probability. So, if we were to toss a fair coin, what's the probability that a head comes up? What's the probability that a tail comes up? So, I think we know the answer to this already, and that it's 50-50. The key here is introducing the word fair, meaning that this isn't doctored anyway, it's not chipped. You're just as likely to get heads as you are to get tails. And so we know just from experience, heads is 50% and tails is 50%. All right, so now we're going to dive into this section of probability for much more complicated things and how we would figure them out. So the first thing you need to know how to do is to construct probability models. All right, so here's what we're doing. The probability model has a sample space. A sample space is all of the things that can happen, so you would write this out. For flipping a coin, the sample space would be heads, tails. You just write them out. All right? Then, what's the probability? Well, we'll get to that in 1 second, but the probability of heads, we use P for probability, so probability of heads has to be greater than or equal to 0. The probability of tails has to be greater than or equal to 0, so you can't have negative probability. And if we were to add these together, P tails plus P heads, you better get 1. So if you add up all the things that could happen, you need to get 100%, which we represent as 1. All right, so we've got a bag of M&Ms. The candies are colored red, green, blue, and brown, yellow, and orange. Suppose that a candy is drawn from the bag and the color is recorded. That got cut off. The sample space of this experiment is red, green, blue, brown, yellow, orange. So those are all the things you could get. Determine which of the following are probability models. All right, let's start down here. C's out. You can't have negative probability. Let's go with this one. 30, 45%, still 45%, 50, 60%, 80%, 100%. All right, so we are in business. That is a probability model for this bag of M&Ms. How about this one? 10, 20, 30, 70, 90, 120%. No good. Get it out of here. Last one. This, while it looks a little fishy, is absolutely a probability model because every single one is either greater than or equal to 0. And if you add them all up, you get 1. All right, try problem 7. Okay, so the experiment consists of rolling a fair die once. A die is a cube with each face having either 1, 2, 3, 4, 5, 6. Construct a probability model for this experiment. So if we look back here, we're going to say outcome and probability. So again, we'll say this up at the top, outcome. Let's start with that. What are the outcomes? We could get a 1, a 2, a 3, a 4, a 5, or a 6. So everything that's in your sample space. What is the probability? 1/6, 1/6, 1/6, right? It's equally weighted between all of them. You have a 1 out of 6 chance to roll each number. So that's what your probability model would look like for a single die. Try problem 23. Okay, an experiment consists of tossing a coin. The coin is weighted now, so that heads is 3 times as likely to occur as tails. Construct a probability model. Outcome. You can still get either heads or tails, but now the probability is much different. All right, so what's the probability of getting a heads? 3 out of 4, or 0.75. You can write it either way. You got a 1 out of 4 chance of getting tails, or 0.25. And that's it. That's all the outcomes and the probabilities. Try problem 27. Okay, so let's compute probabilities of equally likely outcomes. We have a formula. The formula for probability is the number of times that something that you want to happen happens divided by the total number of things that could happen. I like to think about this as good stuff over total stuff. All right? Number of ways that the thing you want can happen divided by all the possible things that can happen. All right? So calculate the probability that in a 4-child family, there are 3 boys and 1 girl. All right, to do this, we need to find the sample space. All right, so in this situation, what are some of the outcomes? And we can do a little chart here. Boys and girls. All right, you could have 0 boys and you could have 4 girls. All right, and we could work all of that through. But assume equally likely outcomes. So this is a little bit tricky here, because on this one, does the order matter? It does. If you went girl, 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 boy, and then girl, girl, boy, girl, 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 boy, boy, we need to list all the different things that can happen here. All right, so we have girl, we'll switch this to boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, girl, boy, boy, boy. Right, so we've got those options, and then we're going to switch this last option over to boy, but it's going to be the exact same thing again, repeated. So we're going to have boy, and then girl, girl, girl. We'll have boy, girl, girl, boy. We'll have boy, girl, etc., etc. Let me get them all down. Oops. Boy, 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 girl, and last one is a family of 4 boys. All right, so we want 3 boys and a girl. Let's find all the places that that happens. There's 3 boys, there's 3 boys, there's 3 boys. How else does it happen? There's 3 boys. Anywhere else? Nope, that's it. So there are 1, 2, 3, 4 ways to have 3 boys. And there are 16 total choices. Now, this 16 should look familiar from 14 too. Remember that this is the n to the r formula. We have 4 things that could happen, and we're picking how many things in each case? Just 2, right? Boy or a girl. So 4 births, and there's 2 choices each time. That's 16. All right? Okay. Let's talk about try 37. All right, so let's consider the experiment of drawing a card from a standard 52-card deck of playing cards, ace through king, 4 suits. So we've got diamonds, we've got spades, we've got hearts, and we've got clubs. E is representing the event draw heart. So E is heart, and F is drawing an ace. All right, write the event E and F. All right, so E is, sorry, we've already done that. All right, but what about E and F? I want to draw a heart and an ace. Okay, so that's going to be the ace of hearts. There's only one card that's a heart and an ace. What about for B? I want an ace or a heart. Okay, so it's going to be all 13 hearts plus the ace of spades, the ace of diamonds, and the ace of clubs. Notice how the ace of hearts is already in this one, so we don't have to write it again. All right, let's compute the probability of E happening. So how many hearts are there? We know that already. 13 out of 52. So 1/4. What's the probability of F happening? Okay, so there are how many aces? There are 4. So that's 1/13. Let's get into slightly harder here. So this is, I want them to happen at the same time. All right, so this you can think of as the word and. So the probability that E and F happens, how many times does that happen? Just once. 1 out of 52. So this one here is going to be the word or. How many times does either you get a heart or you get a ace? An ace? Well, we've counted them here, 13, 14, 15, 16 of them out of 52. Let's divide that by, does it go in evenly? Let's see. 8/26, 4/13. There you go. Okay, let's find the probability of the union of two events. So we've just seen it actually already. The union here, this is the OR word. What we can do here is we can add up, and this is what we did before. We can add up all the diamonds. We can add up all the aces. But then we have this minus thing here. Minus out the ace of hearts. Sorry, diamonds. Saying the wrong one. The reason why is that the ace of diamonds was counted here, and the ace of diamonds was counted here. We got to subtract out one of them because we don't want to count it twice. So no double counting here. Let's try this. If there's a 30% chance of E happening, a 40% chance of F happening, and a 20% chance that they both happen at the same time, what is the chance that either one, E or F, happens? So here we go. We're going to say 30 plus 40%, but then subtract out the 20% of the time that they're happening together. So this is 70 minus 20 is 50%. Try problem 45. All right. Now, mutually exclusive means that they can never happen at the same time. All right? Never at the same time. So in that case, you don't have to do the minusing because it would never happen that they show up at the same time. So we just get to add them. All right, so in this case, if E and F are mutually exclusive, then you just add them together and you would get a 50% chance that either one happens. Try problem 47. All right, last objective, I believe, might be one more. Use the complement rule. So the complement rule means that all your outcomes have to add up to 1. So the probability that the complement would happen is 1 minus the probability that the original event would happen. All right? Oh, there it is right there. If there's a 30% chance that it rains tomorrow, what's the probability it won't rain? Probability of no rain is 1 minus probability of rain. Makes sense. 1 minus 0.3. You got a 70% chance that it'll rain. Try problem 51. Okay, last thing we're going to do here is probably the most complicated thing we'll show you. See if you can bear with me here. What's the probability that in any group of 5 people, we'll start small here, at least 2 of them have the same birthday? All right, we're assuming no leap years here. The best way to figure this out is instead of saying what's the probability at least 2 people have the same birthday, is the complement of nobody has the same birthday. Right? Because if nobody has the same birthday, that's the opposite of at least somebody has the same birthday as somebody else. So let's figure this out. We're going to just calculate what this is here. What's the probability that nobody has the same birthday? Well, what's the probability that the first person has a birthday? 100%. What's the probability that the next person has a birthday? So we're doing this AND thing, so we're going to multiply. In this case, the probability that nobody has the same birthday, well, what's the probability the second person has a different birthday? There are 364 days that would be different than the first person. The next kid, 365. Oops, sorry. That's the denominator. 363 different days than the first 2 people. The fourth person, 362 out of 365 possible days. And the last person, 361 out of 365 days. All right, so let's grab the calculator here. And where'd you go? Get rid of you. All right, so on this one, the numerator is going to be 364 times 363 times 362 times 361. And we're going to divide that by 365 to the 4th. And we get 97%. So there's a 97.2% chance that we don't have the same birthday, which means that in 5 people, there's a 2.8, 2.7% chance that somebody has the same birthday. Now, as I bet you can guess, this number gets bigger pretty fast because there's a lot of multiplying going on here. So let me erase this so you can see the numbers. And you'll see here that it only takes about 23 people, right here, for there to be a 50-50 chance that somebody's going to have the same birthday as somebody else. If you get up to 90 people, it is almost guaranteed that 2 people in that room will have the same birthday. Right? You don't have to get to 365 for that to happen. All right, wrap things up with problem 71, and you are home free. Questions, we'll go over them in class. Good luck.